Good morning to one and all. My name is Manoj. I am first semester from Information and Technology. Subject is essential and problem solving. Topic was pairs with sum. Problem definition. Define with pairs with some problem. Given give an array of integers and target sum, find all unique parts pairs that sum to the target. This problem is foundational in algorithm design and appears to coding interface, comparative program and embedded systems. Applications include collision detection, cryptography and data integrity checks in IT systems. Formalize the input as array and A of size n and target sum as output as a set of pairs I and j, where ai plus aj is equal to s. Brute force approach. The naive solution uses nested loops to check all pairs I and j, resulting in OM square time complexity. For each element ai, iterate over aj where j is greater than I to avoid duplicate pairs. This approach is inefficient for large arrays. N to the n is greater than 10 to the power due to quadratic growth. Hash map optimization. Use a hash map to store elements as keys and their insides as values, reducing lookup time. For each element, compute complement C is equal to S minus AI and check if C exists in the map. If found, a valid pair is identified in on time with on space. This method is widely used in practice due to its balance of speed and simplicity. Two power technique requires sorting the arrays first, then using left and right pointers at boundaries. If sum of a left plus a right is less than s, increment left. If if greater than s, decrement right. Repeat until pointers meet, yielding on post short travel transversal time. Handling duplicates. Duplicates can lead to redundant pairs. Use data structures that enforce unique sets. In hashmap approach, stores only the latest index to avoid recomputation. Duplicates may be valid if indices differ, but pairs are equivalent. Formalize output as a set of tuples and ensure mathematical uniques. Edge case engineering. Empty array return empty result. Validate input size before processing. Single element array. No pairs possible. Handle with early termination. All elements equal only possible if 2 into ai is equal to s. Check once and compute combinations. Negative numbers algorithms must handle sign arithmetic correctly. Algorithm pseudocode. Initialize empty hash map and results set. For each element, compute c is equal to s minus ai. If c exists in a map, max to result. Insert a into map with index I. Return result set after full transversal. Algorithms pseudocode in two pointer. Sort array A in non-decreasing order. Set left is equal to 0, right is equal to n minus 1. While left is greater than less than right, compute sum. If sum equal to s and pair and skip duplicates, add pair and skip duplicates, else adjust pointers. Return result set after loop termination. Highlighting sorting as a loop invariances for correctness. Complexity and analysis formulas. Brute force is equal to T of n is equal to summation of I equal to 0 to n minus 2 into sum of j is equal to I plus 1 to n minus 1 into 1 is equal to n into n minus 1 by 2. Amortized analysis has a hash map average 0 per operation worst case. Use master theorem to analysis recursive variantations. Memory access patterns. Hash map. Random access via hashing cache inefficient for large tablets. Two pointer. Sequential access post short cache friendly and predictable. Brute force. Nested loops with straight one axis but high latency due to branching. Spatial locality improves two pointer performance on modern CPUs. Consider prefetching in high performance systems to hide memory latency. Parallelization strategies. Brute force. Parallelize outer loops across threads, each checking inner loop independently. Hash map. Use thread safe structures or lock free techniques to avoid race conditions. 2 point. Inherently sequential but sorting can be parallelized. Map reduced paradigm. Paradigmization array compute local pairs merge results. Scalability limited by Adamahal law. Identify parallelizable sections. Applications in IT systems. Used in network packet analysis to detect duplicate checksums or collisions. In database systems, find record pairs matching a conditions. Cryptography. Identify key pairs in key exchange protocols or hash collisions. Data mining. Find co-occurring features in large data sets. Real-time systems. Optimizes your low latency response in embedded devices. Variantations and extensions. Threesome find triplets with some s. Extend two pointer with outer loop. Closest pair. Minimize or use a two pointer with distance tracking. Count pairs. Return number of pairs, not the pairs themselves to save memory. Range constraints. Pairs must satisfy and filtering logic. Implementation pitfalls. Integral overflow. Use larger data types or bounds checking when summing. Hash collisions. Choose robust hash functions and resizing strategies. Off by one errors ensuring pointer bounds to loop termination conditions are correct. United duplicates validate output format and use canonical pair ordering. Testing and verification. Unit tests cover edge cases, empty, single, duplicates, negative, large numbers. Benchmarking measure execution time versus input size to validate complexity. Invariant checking verify some property and uniqueness in output. Hardware considerations. In microcontrollers prefer to pointer due to limited RAM. In GPUs parallelize brute force using CUDA or OpenCL for massive arrays. Memory bandwidth hash map performance degrades a large tablets due to cache misses. Power efficiency. Minimize operations in battery powered devices. Case study in embedded systems. Scenario data array find pairs indicating system anomalies. Optimized by pre-sorting data during ideal circuits to reduce latency. Valid with worst case input size and measure power consumption. Thank you.